So, what if I told you that pressure and temperature, well, they aren't exactly what you think they are? Today, we're diving deep into the invisible world of gases to solve a puzzle that's centuries old. See, we knew the rules they followed for a long, long time, but nobody could figure out why. So, let's get right into it. The source material for this explainer kicks off with this absolutely perfect analogy. And we've all been there, right? Especially during exam season. The less space you have, the more pressure you feel. It's such a common human feeling, but it turns out it's also the exact principle behind one of the oldest laws in all of physics. So, yeah, what does a stressed out student have to do with, say, a container full of oxygen? Well, as it turns out, that very same relationship between space and pressure. It's actually a fundamental rule of the universe. And for us, it's our very first clue in this whole investigation. Okay, so to even begin to figure out the super complex rules of real gases, with all their messy, complicated interactions, physicists did something really clever. They basically said, let's just imagine a perfect, super simplified version first. And that thought experiment, that's what we call an ideal gas. Now, let's be super clear. An ideal gas doesn't actually exist anywhere in the universe. It's a completely theoretical benchmark, a perfect little model. But the genius of it is, by studying how this perfect gas is supposed to behave, we can finally start to make sense of all the real gases that are all around us. The source material has this great way of putting it. Think of the ideal gas as a sort of role model, something to aspire to. Real gases, of course, can never quite live up to this perfect standard, but under the right conditions, they can get surprisingly close. So what makes this gas so ideal? Well, it all comes down to three pretty simple assumptions. First, its particles are basically just tiny points. They take up zero space. Second, they don't attract or repel each other at all. Absolutely no drama between them. And third, whenever they collide, they bounce off each other perfectly, kind of like billiard balls, without losing a single drop of energy. Okay, so now that we have our simplified model in mind, let's look at the simple rules that these ideal gases follow. And you should really think of these as the first clues that scientists started to pick up on. These were observations they were making for centuries before they had any clue why they were happening. And our first clue takes us way, way back to 1662. It's called Boyle's Law, and it's super simple. If you can keep the temperature steady, then pressure and volume are total opposites. It's just like our student analogy, right? Less space equals more pressure. Here's an easy way to picture it. Imagine you're pushing down on a piston in a cylinder, like a bike pump. The more you squeeze that gas into a tinier and tinier volume, the harder it pushes back against you. That feeling? That's Boyle's Law in action, right there. All right, next up we have Charles' Law. This time we flip things around. We keep the pressure constant, and instead we play with the temperature. And the rule is just as simple. As the temperature goes up, the volume goes up. You heat things up, they expand. Easy enough. And our source material gives another great, really simple example. Just making a pot of tea. As that water heats up, it starts to bubble and rise, right? It's taking up more and more space in the pot. You are literally witnessing Charles' Law right there in your own kitchen. Now, here's where it gets really cool. When you combine Boyle's Law, Charles' Law, and a couple of others, you get this, the ideal gas law. This one, single, really elegant equation ties pressure, volume, and temperature all together. And for the first time, scientists could actually predict how gases would behave. But there was still this huge, nagging piece of the puzzle missing. Why? Why did it all work? And that question, why, brings us to the main event of our story. We've seen all the rules, the what. Now, finally, it's time for the why. This is the moment when a brilliant new theory came along and explained everything that was really going on underneath the surface. So really, why does squeezing a gas make its pressure go up? And why does heating it make it expand? The answers, it turns out, aren't in the big stuff we can see and measure. Nope, they're hidden away in the frantic, completely invisible dance of trillions and trillions of tiny particles. We have to go microscopic. Okay, here's the breakthrough. Just picture one single gas particle hitting the wall of its container. It's just one tiny little impact. But it bounces off, and that tiny little bounce exerts an unimaginably small force. Now, imagine that same thing happening trillions upon trillions of times every single second, all over every single surface of that container. That relentless combined storm of tiny little impacts,
That is what we feel as pressure. And all of that logic can actually be captured in this one really powerful equation. Now, I know it might look a little complex, but the idea behind it is actually incredibly simple. It just shows that the pressure, the P, that you feel depends on really just two things. How many particles are packed into the space, that's the density, and how fast those particles are moving, that's their velocity. That's it. More particles or faster particles means more collisions, which means more pressure. Motion literally creates pressure.
So now we have this really powerful new theory on our hands. The final test, the big moment, is to see if this one core idea, the idea that pressure is just a bunch of particle collisions, can explain all those rules we saw earlier. It's time to connect the dots. And right here, this is probably the most profound, mind-bending insight from this entire theory. It completely redefines what temperature even is. See, temperature isn't just some abstract idea of hotness. At the microscopic level, temperature is motion. It's nothing more than a direct measure of the average kinetic energy, the average speed of the particles. That's it. More heat simply means the particles are moving faster.
And once you have that amazing insight, everything just clicks into place. Think about it. If the temperature is constant, that just means the particles' average speed isn't changing. So if you shrink the volume they're in, they're obviously going to hit the walls more often, which increases the pressure. Boom, just like that. The kinetic theory doesn't just agree with Boyle's law, it proves it, right from the first principles.
Okay, I know what you might be thinking. This is a really beautiful theory and all, but so what? Does any of this actually matter in the real world? And the answer is a huge yes. Because once you understand the microscopic cause of something, you can start to make incredibly precise predictions about the world you can actually see.
For example, we can actually use this theory to calculate the typical speed of gas particles. It's called the RMS, or root mean square velocity, which is just a fancy way of finding the average speed for a bunch of things moving around randomly. And the result is, well, it's pretty mind-blowing. The air molecules in the room with you right now are zipping around at an average speed of about 500 meters per second. That is over 1,100 miles per hour. We're talking faster than a speeding bullet.
So let's wrap this up with the key takeaways, right? First, pressure isn't some mysterious force. It's just the combined result of countless microscopic collisions. Second, temperature isn't just a number on a thermometer. It's a direct measure of how fast molecules are moving. And finally, the kinetic theory is the beautiful, elegant bridge that connects the invisible world of particles to the visible world we experience every day. And all of this leaves us with one final, really fascinating question to chew on. If temperature truly is motion, then what happens at absolute zero, the coldest possible temperature in the entire universe? What happens when all that frantic molecular motion just stops? When it all grinds to a complete halt? What would that even look like? That's a thought for another time.